Again, welcome to Mathematical Structure for Computer Science. This is CS113, also known as Discrete Mathematics. In these lectures, we're going to discuss about recursive definitions and structural induction. These lectures cover our course textbook, Chapter 5, Section 3. So our main objective, again, is to define the concept of recursive functions. So recursively define functions. Also recursively define sets and structures. We should also go through structural induction and generalized induction. So first, we start with the definition. And we say a recursive or inductive definition of a function consists of two steps. The basic step, which specifies the value of the function at 0, and also the recursive step, giving a rule for finding its value at an integer from its value at smallest integers. And the rule, again, the rule can be any problem. For example, we know to find a factorial of a number, we can use the recursive concept, or to find a Fibonacci or merge sort. Because in terms of factorial, we know factorial of 5 means 5 times 4 times 3 times 2 times 1. So we can see that we are repeating the same thing over just by reducing by 1. And that's the concept of recursion. Actually, that's what we call the concept here as a recursion or recursive, the reoccurrence of an event. Now, if I want to find addition of, let's say, 1 plus 2 plus 7 plus 15, well, I can't use the recursion here because I can see the difference between the values, or the interval between the values are not the same. 1 plus 3 plus 20 plus 25, they are not the same. But I can use recursive concept to find addition of a numbers. Example, 1 plus 2 plus 3 plus 4, or 2 plus 4 plus 6 plus 8, because I can see the intervals are the same. So that means I'm doing the same function, but when I add 2 to one value, when I get the answer, I add another 2, I get the answer, I add another 2. Or add 1, when I get the answer, I add another 1. So I'm adding the same value up to wherever I want to reach. So in this case, I can be able to use the recursive concept. So just by looking at the definition here, we can see that recursive and inductive are almost the same. It's 2 steps. We need to know the basic step and also the recursive step. So a function f at n is the same as a sequence A0, A1, where AI, and where we say also f at I equal to AI. This was done using recurrence relations. So the example will be here, addition of 1 plus 2 plus 3 plus 4. So we are adding 1 to each next value. We are adding 1 to next value. So that will be a sequence. The rates of changes from A0 to A1 to A2 to A3 is the same. So if it's the same, then we can use the concept of recurrence relations. Now, hopefully the example here will create our definition for us. So this is a recursively defined function. So the example here said we have a function f at 0, and the answer for f at 0 is 3. Then we have another function f at n plus 1. F at n plus 1 is 2, f at n plus 3. Now they say we should find f at 1. F at 1 means when n is 1, which means it will be f at 1 plus 1, it will be f at 2. Then we're also going to find f at 2, f at 3, f at 4. So first we start with the f at 1. Well, we know that f at 0, 0 comes before 1. So we know f at 0 is what? 3. Now, to add it from this definition here, we saw that if we had 1, f at n plus 1 more, it will be f at n plus 3, which means every run we are going to add 3. So if I reach f at n plus 2, it will be 2f at n plus 3 again. So here, to find f at 1, it will be 2 f at 0, because 0 comes, then the next value. So 2f at 0 plus 3. So we know f at 0 is 3. Then we have plus 3. When we add all this, we get 9. So this is a recursion because we know f at 0 is 3. And we have a condition here. This tells us what number we had to each sequence. For example, if it's 1 plus 2 plus 3, I know that I'm adding, moving sequentially from 1 to 2 to 3 to 4. And here I can see that, okay, we are moving sequentially with plus 3. So if I'm finding f at 1, what is f at 0? F at 0 is 3, so I'll plug f at 0 here. So I'll get 2 and then f at 0. But f at 0 is what? 3. So it will be 2 times 3 plus 3. Now I'm looking for f at 2. Now in order to look at f at 2, then it should be what? F at 1 plus 3. F at 1 plus, because we are in 2 now. Here we are in 0. We look for f at 1. Now we are looking for f at 2. In order to look for f at 2, it will be f at 1 plus 3. But the formula is 2 f at 1 plus 3. Because here we can see n plus 1, which means to go to the next value, I will take the previous f at n, then I'll multiply it by 2, then I'll add it to 3. So f at 1 means I'll take the previous value. If I'm 1, the previous value should be 0. So f at 0 is 3. So it's 2 times 3 plus 3. Now I'm f at 2. F at 2 means the previous value is f at 1. So I'll multiply 2 by f at 1, which is 9. So we get 2 times 9 plus the 3 is 21. Now if I'm looking for f at 3, the previous value based on this formula, I'm f at 3. This should be f at 2 because 3 is n plus 1, which is 2 plus 1. So which means here should be 2. So I'll multiply f at 2 value to 2 plus 3. And that's what we did here, 2 times 21 plus 3. Now f at 4 means n plus 1 is 4. So it means 3 plus 1 is 4. So 2f at n here should be 3. And I know 3 is 45. So we get 2 times 45 plus 3. So that's 2 times 45 plus 3, which gives us 93. So this is the concept of recursive. Because you can see we are using the previous value to get the next value, adding the same 3 to the previous value, but we have every round we have to double the function value because the formula is 2fn. If it's only fn plus 1, fn plus equal to fn plus 3, then it just means that we had 3 to the next previous value, we get next value. We had 3 to the previous value, we get next value. But here the formula is 2fn. So we have to double the function value, then we add to 3. So if I'm looking for f at 4, f at 3 is 45. So I'll multiply 45 by 2, double it to 90, plus 3, which will be 93. Now let's look at the next example. Here they say we should give a recursive definition of the factorial function. So in theory, a factorial of 0, so that's again the basis. Remember, the basis step should be the lowest point we will reach, the minimum point we will reach. So of course we can find a factorial of 0. Factorial of 0 will give me 1. And also factorial of 1 is 1. This is the regular and the rule of a factorial numbers. So this means I can say the base step will be factorial of 0 is 1, or factorial of 1 is 1, since both of them are the same. Then in order to get the next value, let's say factorial of 1, it will be the factorial of the 1, that very 1, times the next previous one. But again, when I'm 1, the only thing is only 2. Factorial of 1 means 1 times 0. I'll lower. So that's what we have here, n plus 1 times f at n. So if I'm looking for factorial of 1, then it will be 1 times the previous value, because we are n plus 1. So the factorial of 6 means 6 times 5 times 4. We reduce it all the way to 1. So this is the definition. Lowest unit, which is the basic step, f at 0 should be 1. So the next n plus 1 value, if this is 6, then it should be 6 times 5. Then we reduce it times 4, we reduce it until we reach 1, which is the basic step, then we stop. So this is again the recursive defined functions. We had the symbols here. They say we should give a recursive definition of a sum k from 0 to n ak. So from 0 to n ak, what this means is that we're going to multiply a0. We start from 0, so a0 times a1 times a, oh sorry, this is summation. So it will be a0 plus a1 plus a2 plus a3 all the way to plus ak. Again, give a recursive definition of summation. This symbol stands for sum. We will see the example of the product symbol also. So this means again we start from 0 to n, just adding the a0 plus a1 plus a2 all the way to plus ak. And that's the solution here. The first part of the definition will be, we say k from 0 to 0. So it will be only one value. Whatever a0 is, that's it. So that will be our base case, the beginning value. Then the second part, which will be the recursive step, it will be, we are in ak. So it will be ak, let's say k is 6, times ak minus 1 times ak minus 2. I'm reducing it. I'm starting from highest to lowest. But here we say, okay, from k0 to n plus 1 ak, which we can say k to from 0 to n ak plus the one value is n plus 1 is out, so plus a n plus 1. So this will be recursively. So if it's a summation, we say, okay, ak, let's say we start from 0. So a0 plus a1 plus a2 plus a3 plus up to ak. Or ak plus ak minus 1 plus ak minus 2 all the way to when ak will be 0. So this example of a Fibonacci numbers. And the concept of a Fibonacci numbers is that we are going to add the two previous value to get the present value. But when we start a value from 0, there's nothing in the front. So Fibonacci of 0 is 0 because 0 is by itself, nothing. That's why we write f(o) equal to 0. Then Fibonacci of 1 will be 1. Because even if we are adding the previous value, there's no previous two values. So 0 is 0, 1 is 1. Then when we have 0 and 1, two previous value now, we can find the Fibonacci of n will be n minus 1 plus n minus 2, which means the previous value plus two previous values. So if I'm here and this is f2, and I'm looking for Fibonacci of f2, then it will be f1 plus f0. Why f1? Because n is 2, 2 minus 1 is 1. Why f is 0? Because n minus 2, 2 minus 2 is 0. And f0 will be the 0 here. So that means Fibonacci of 2 will be 0 plus 1. And that's what we have here. Fibonacci of 2 will be f1 plus f0, which will be 1 plus 0 is 1. Fibonacci of 3 will be f2 position plus f1. So again, always the two previous values. Fibonacci of 4 will be 3 and 2. 5 will be 4 and 3. So we had the previous two values. So that's why we have 1 plus 0, then 1 plus 1, then 2 plus 1, then 3 plus 2. So if I'm looking for Fibonacci of 6, then it will be F5 plus F4. So again, the concept of Fibonacci is adding the two previous values. Then you get your present value. Now, if there's no any value in the previous, which means F0, then the answer will be 0. If it's F1, the answer will be 1 because the previous value is 0 plus the present value. So next we talk about recursively defined sets and structures. And here we said that the recursive definitions of sets have always two parts. We said the basis part. The basis part or the step is what gives us the initial value, the beginning of the condition. So let's say, again, I'm finding a factor of 7, then the lowest will be 0 or 1. Because factor of 0, the reason why it's 0 or 1, because factor of 0 is 1, factor of 1 is 1. So 0 or 1, the answer is the same. So again, the two parts. The first is the basis step, which will specify initial collection of elements. Then we have the recursive step or part, which gives the rules for forming the new element in the set from those already known to be in the set. So a factor of a number, the rule said you multiply the numbers in sequential order. So if you have a factor of 5, it will be 5 times 4 times 3 times 2 times 1. So which means the initial collection or the smallest unit is 1. So the basic step will be factorial equal to 1, then it's 1. Then recursive step, you start from 5, reduced by 1. So 5 times 4 times 2, 5, 4, 3, 2. So we say the recursive step gives the rules. The reason why we use the term rules here, factorial is a different way of solving it from Fibonacci. It's a different way of solving it from merge sort or finding addition of numbers or product of numbers in sequential order from 1 to 50. It's a recursive because I mean to say 1 times 2 times 3 up to 50 or 1 plus 2 plus 3 up to 50. But they all have different rules of arriving to the final answer. So here we say sometimes the recursive definition has an exclusion rule, which will specify that the set contains nothing other than those elements specified in the basis step and also generated by application of the rules in the recursive step. And we will always assume that the exclusion rule holds always, even if it is not explicitly mentioned. Again, we will later develop a form of induction called a structural induction to prove results about recursively defined sets. So we have an example here also about sets and structures. So example given here, if we have a subset of integers S, the subset of integers S, the basis step we say 3 belongs to X. And the recursive set we say, okay, if X belongs to S and Y belong to S, then S plus Y is in S also. So we can see our rule here. If we have two terms, let's say 2 belongs to the set S and 3 belongs to set S, then we are saying that 2 plus 3, which is 5, 5 also should be in set S. So here we say initially 3 is in the set S. If that is the case, we get 3 plus 3 equal to 6, then 3 plus 6 equal to 9. So we are adding 3 to the previous values. Then another example about natural numbers n. So natural number, we know we start from 0. So the basic step will be 0 belongs to n. Now the recursive step, we say that, okay, if lowercase n is in uppercase n, then n plus 1 also is in n. So your initially 0 is in s, so 0 plus 1, 1, then 1 plus 1, 2, then again 2 plus 1, 3, etc. will be in. Next, we talk about strings. Again, in computer science, we say strings are normally characters, numbers, symbols that are in double quotation. And we cannot do arithmetic operation on strings. But for example, we can join two strings together. We can sort the elements in the strings, etc. So here we say we have a sort, we have a set. We have a set of a string over the alphabet. So in this case, the basic step will be lambda belongs to the string. Lambda belongs to the string. So what we are trying to say is that the meaning of lambda is the empty string. So the basis unit, since the string can have the smallest unit of a string, means when there's nothing, no character, nothing, which we call the null or empty string. So now if we have a string that have 0, 1, and the strings here are a set of all bits string, then first, this is 0 and 1. We want to say the possible substring we can get from it. So we can get empty string, which is the lambda. Then we can get again 0 and 1. Then we can get 0, 0. We can get 1, 0. We can also get 1, 1. And these are the substrings. So example given here, if I have a string AB, which will show that AAB is in the string also. So we know the basic step will be lambda because lambda stands for empty string. So we say if empty string belongs to the string and A belongs to the string and A belongs to the empty string star. Now we can say that A belongs to the star and A belongs to the summation here, the string, substring, and A also belongs to the star. And since AA belongs to the star, then B belongs to the star because AAB again belongs to the summation, the string star. We can also do a string concatenation. The concept of string concatenation is to join two or more strings together. So we say two strings can be combined via the operation of concatenation, is to join or combine two strings together. So if we have summation sign be the set of symbols and summation star be the set of strings formed from the symbols in set of string. Here we can define the combination of two strings denoted by apostrophe, denoted by a period here, recursively as follows. So we know the basis step will be the smallest unit. So we said if W belongs to a string sub, then W, remember lambda is empty. So W with empty, we give us W. Again, this is the smallest unit for. Now, in terms of recursive step, we can see that we say W1 belongs to the star summation. W2 also belongs to there, and S belongs to the summation. Then we have W1 times W2X, which will give a W1 times W2 and X. And often W1 and W2 is written as W1, W2. So if W1 is ABRA and W2 is CADABRA, then the combination of the two strings, W1, W2, will be addition, adding them together. So we get ABRA, which is W1, then ACADABRA, which is W2. So concatenation here, we can see that means to join two strings together. Also, we can determine the length of a string. So here, given a recursive definition of LW, the length of a string W can be recursively defined by if the length of lambda is an empty string will be 0. So the length of WS will be the length of W plus 1. Again, if W belongs to summation star or belongs to the summation, which is the string. So this is a well-formed formula for propositional logic. We know that the set of a well-formed formula in propositional logic always involve true-false propositional variables, always true-false, which is the binary numeric system, 0 ones, 0 is false, and then 1 is true. But in the propositional logic, we know we have some operators, and also a variable will be, again, the alphabetical values or a symbol. But here we should know the operators in propositional logic. As we said, we have negation, conjunction, disjunction, implication, and biconditional. So if we are again trying to use the concept here in a well-formed formula in propositional logic, we can say the basic step will be true or false. And also S. Here we say the S is the propositional variable and they are well-formed formulae. So the recursive will be the basic step, the lowest stage. But the recursive step will be if E and F are well-formed formula, then not E, then E and F, or E or F, or if E, then F, or if and only if E, then F are well-formed formulas. Here, what we're trying to do again, we are using the propositional logic operators. So a good example given here, we say that, okay, if we have P conjunction Q implies to Q conjunction F. Again, P disjunction Q imply Q conjunction F. Or we say if P or Q implies to then Q and F. So next is the rooted trees. Here we see a set of rooted trees where a rooted tree consists of a set of vertices containing a distinguished vertex called the root. And edges connecting these vertices can be recursively by this step. So we can use the recursion. And the whole concept is the diagram. The diagram will tell us. So what we mean here in computer science, the root of a tree is at the top, not bottom. So here, always we begin with the root. If we are creating a new tree, a tree always have to have a root. So the basic step will be the root one. Then step one, maybe we are creating level 1 items. That's inserting the left and right charts. Then step 2, we move to level 2 to insert again children. Then level 3, the same thing, we keep going. So here we are building up a rooted tree starting from the root. The root is at the top and we keep going down. We can also have what we call the full binary tree. So a set of a full binary trees can be defined recursively by this step. The basic step, there's a full binary tree consists of only a single vertex. So that will be our basis. At least we have only one vertex. It can be the root. Because if we don't have no root, we cannot again build a tree. So the basic step is there's a full binary tree consists of only a single vertex R. Since it contains only one R, again, that's our root. And also that will be the basis, the smallest unit. Then recursive will be, again, if it's T1 and T2 are disjoint full binary tree, then there's a full binary tree denoted by T1, T2. Consists of the root R together with the edges. Edges are the line that connect the vertices together. So in our diagram previously, this would be the edges. So we also have the full binary tree, as we said. A set of full binary trees can be defined recursively by this step. So we saw these two steps. There's a full binary tree consists of only one single vertex R. So in the smallest unit, we should have only one vertex, which is the root. Then the recursive step, if we have T1, T2 are disjoint full binary tree, then there's a full binary tree denoted by T1, T2, and which will consist of the root R with edges connecting the root. And we talk about building up a full binary tree. So we start with the root, we finish with the first level, then step 2, we go to the second level. So next is the structural induction. So in structural induction, we said that to prove a property of elements of a recursively defined set, we always use structural induction. Again, to prove a property of the element of a recursively defined set. So the basic step, we need to show that the result holds for all elements specified in the basic step. Then secondly, we need to show that if the statement is true for each of the elements used to construct, again, we should show that if a statement is true for each of the elements used to construct a new element in the recursive step of the definition, the result holds for this result elements. So the validity of the structural induction can be shown to follow from principles of mathematical induction. So that's the whole concept of structural induction. And also the validity of structural induction can be shown to follow from principles of mathematical induction, as we said. So structural induction also have two steps, the basic step and also recursive step. And we need to prove a property of the element of recursively defined set. We always use structural induction. So this will be the conclusion of our lectures on the concept of recursive functions. Here we didn't do much, it's just to understand the concept. And I think in programming language or data structure, we also have a recursion functions or concept. And we may discuss that in our next lectures. In our next lecture, again, we are going to cover recursive algorithms, mostly the algorithms used in computer science. So in this lecture, we just focus on the mathematical aspect and also the definition of it. So again, wish everybody the best and thank you.